Hi everyone. Thanks Hannah for the introduction. And today we'll be talking about the Neopotent Theorem. And as an application, I will prove a theorem I stated yesterday about the thick subcategory theorem. All right. So let's define something called a field. We say that a ring spectrum E is a field if its homotopy groups is a graded field. And for example, every Morava K-theory is a field. So we know that pi star of Kn is isomorphic to Fp and Vn plus minus 1. And for people who haven't encountered the notion of graded field, you may feel that this is not a field because, for example, 1 plus V is not invertible, but in algebraic topology or in the graded setting, we don't consider non-homogeneous elements. This is in degree 0, and that is in degree n or negative n. Then it's non-homogeneous. Therefore, we don't consider these elements. And so, if you only consider homogeneous element, you only have 1 Vn squared, etc. You see that all of them are invertible. Therefore, it's a field in this sense. And therefore, all Morava K-theory are fields. And conversely, if E is any field, then we claim that E has the structure of Kn module for some n. N can be equal to infinity. It suffices to show that E tensor Kn or E smash with Kn is non-zero for some n because of the following, that the proposition is if E is any field and suppose that the smash product with Kn is non-zero, then E admits the structure of a Kn module. In this talk, we are not going to prove this. If you are curious why this is true, you can find the proof in Jack Brewery's notes before the notes I'm using today. So in the end, I will give you the reference. Okay, so essentially, at some point of this talk, I will prove that if E is any field, then E tensor Kn is non-zero. Actually, to prove this, we don't require E to be any field, but we'll prove this. Then we will get the claim that any field admits the structure of a Kn module. Okay. Next, before we prove that, we are going to need some Neopotence detection tool. So here the following statements are equivalent. So I'm trying to use a collection of spectra to detect the Neopotence. So if you have a ring spectrum and if X is a homotopy class and whose image in the E homology is 0 for all the spectrum E alpha. So here alpha is just an index, it's not the exponent. It's that for each index alpha, you have a spectrum called E alpha. So if X, the Hurwitz image of X in each E alpha homology is trivial, then X is nilpotent in the homotopy groups and the homotopy ring, because I is a ring spectrum, the homotopy groups form a ring. Okay, so so that's one of the statements. I'm claiming that all the statements are equivalent to each other. Okay, then the second alternate statement is that if R is still a ring spectrum, then
sorry to interrupt. Actually, there is a question in chat.
Does the odd degree of a graded field vanish? That's odd. No, it's odd degree of a grade. You mean when Vn is in odd degree, what happens, right? So if since it's a graded ring, if Vn is in odd degree, then Vn squared is trivial. But yeah, sorry, I'm being stupid here. So Vn here is not in degree n, so I made a big mistake. It's not in here. Sorry for the confusion. Yeah, it's supposed to be. So Vn it must be in even degree. This is like a polynomial ring. It's not exterior. So yeah, so that's the answer. Okay, let's move on. Okay, if where am I? So yeah, so the difference between the second statement and the first statement is that here we are only talking about pi 0 and the pi 0 of R. So if E alpha detects nilpotence in pi 0, it also detects statement. It also detects nilpotence in all pi m. So you can see that statement 1 to statement 2 is obvious. So if E alpha detects nilpotence in pi 0, then because we know all are equivalent, you can deduce that it detects nilpotence for all. Okay, so now let's see what it says in statement 3. So if X is just a spectrum, not a ring spectrum, then so what does nilpotence mean? So if X does not have a ring structure, then you can consider the exterior product. So you consider the exterior product. You can still take the power of X, but it lives. Here we are talking about the exterior one. It lives in the homotopy groups of X tensor with X tensor with X. Okay, so that's statement 3. It's kind of the exterior version of the nilpotence. Then we have statement 4. Still, we do not require X to be a ring spectrum, and we consider. So, and here we are not considering the homotopy groups. We are consider. I mean, not the traditional homotopy groups, which are defined by maps from sphere into the spectrum. Here we are considering maps from a finite spectrum into X. So E must be a finite spectrum. and then the nilpotence is stated this way. So you can still take the power. And again, it's kind of the exterior version that you need both the domain and the target to be the exterior. I mean, to be the tensor product with themselves. Okay, so you can see that this is quite powerful. The last one is powerful, although it looks powerful, although all the statements are equivalent to each other. So you can see the proof in Rory's notes that the first three proofs are relatively simpler or straightforward, and then you have a proof from 4 to 1, then all of them are equivalent. Okay, so this is the this is 4 equivalent statements. So in the future, if we want to prove that this collection E alpha detects nilpotence, we only have to like check it satisfy one of the statements. Okay, so next we are going to introduce the Neopotent Theorem that for any ring spectrum, the kernel of this Hurwitz map from homotopy groups into the MU homology, it consists of nilpotent elements. So I mean, it consists of all nilpotent elements. So this means that according to what we just talked about, the single cohomology theory MU detects nilpotence. So here you might need a bunch of cohomology theories, but this nilpotence theorem says that you only need one to detect the nilpotence elements, which is MU, and this is very strong theorem. It deduces the Nishida nilpotence theorem that we know that for every positive n that the homotopy groups of spheres is nilpotent. And why this is like a very easy corollary, because we know that the MU homology of the sphere is exactly the homotopy groups of MU, which is the largest ring, and largest ring is we know is a polynomial ring over the integers, and it is torsion free, and we know that all the by a theorem of Serre, we know that the homotopy group of spheres are all torsion. So if we map a torsion group into the torsion free group, it must be trivial. So all the homotopy group, all the elements in the homotopy group of spheres in positive degrees are all in the kernel. So by the nilpotence theorem of David, Nash, Hopkins, and Smith, you see that all elements here are nilpotent. Okay, so that's the nilpotence theorem. Next, we are going to introduce another interesting collection of spectra that detect nilpotence, because sometimes although this is powerful, but it's not always that easy to compute the MU homology. I mean, sometimes it's more convenient to use the KN homology, because after all they are fields, right? And they also have some very interesting properties. So in the end, we want to prove this theorem one. So in the end, not in the end of this talk, later in this talk, we'll prove that they satisfy condition 3. So I mean, when I say detect Neopotence, I mean one of the 4 statements, right? All these 4 statements are equivalent. I'm going to prove it using the third one. So which is the exterior version for the Neopotence. Okay. So before I do the proof, I'm going to define T. Here the notation T means that it's the homotopy colimit of this sequence of maps that you keep multiplying X with itself, and then you take the colimit, and that'll be a useful thing in the proof. So I need a lemma first. So let E be any ring spectrum, and then we have the two statements are equivalent again. So if T is a cyclic, T is a cyclic, it means that T is matched with E. Or here in this talk we use the tensor product here. If T's matched with E is trivial, then the second statement is true, and it's actually if and only if. Then the image of X to N vanishes when N is big. When it's big enough. And why? So remember that T is defined by X. So T is the colimit of X. I mean, both the small X and the big X. It depends both on the small case X and the uppercase X. Okay, so this T is a cyclic. That's equivalent to a statement about both the X. Okay, so why? So here I'm going to give to write down the proof. It's simple, kind of simple. So if the first one is true, so let's prove 1 to 2. Then if so, we assume the first one is true, then it's obvious that this composition is not homotopic because the T tensor E is trivial. Then this implies that the S to X tensor N into X tensor N tensor E is trivial. Sorry, let me write it down. Is 0, or maybe let's write non-homotopic. Then this is also non-homotopic for sufficiently large N. Why? Because remember that we define T as the to be the homotopy colimit of this X to X to N, and therefore if the colimit, if the first diagram is now homotopic, then and it's the colimit, then at some point when N is big enough, this one is also now homotopic. So that's why 2 is true. And the inverse statement, so conversely, sorry, if we assume the second statement is true, then we use a trick that T is actually also the colimit of S to x to n, and then x to 2n. Remember that originally we use this diagram x to 2. Now you can like use bigger steps that each time you use x to tensor n. After all, this is a colimit, so you can use this one. You can use a bigger step to get the same colimit. Then because this is trivial, that is trivial, all are trivial, therefore the colimit is also the I think I made a this is right, and sorry, I said something stupid. These are not zero. We are saying that E tensor T is trivial. So this is the colimit of E and to maybe I write T match with E. And this is X and tensor with E, X tensor to N tensor E, etc. And this is the Hurwitz image, right? This is the Hurwitz image. And since we assume the second statement is true, that is exactly saying that all these maps are trivial. So this is trivial, that is trivial, and therefore that is also trivial. Okay, so that's the proof of the lemma. The lemma is saying that there's the lemma is claiming that there is a compact way to say that all the Hurwitz image vanishes. Not all I mean, it's saying that if X is Neopotent in this sense, then it's sufficient to say that T tensor E is trivial. So that's more convenient, right? You, instead of focusing on this element, you can just say that certain spectra is trivial. That's a more compact and convenient way to encapsulate what you want to prove. Okay, so by this lemma, we are going to prove theorem 1. So maybe let me review what theorem 1 is. We are trying to prove that the spectra Kn, I mean the collection of all of them, including 0 and infinity, they detect the Neopotence. Okay. Why? Let's write down the proof. So we assume that the Hurwitz image of X in K so we assume X lives in pi 0, and assume that their images in Kn homology are all trivial. Now our goal is to prove that X, the power of X in the homotopy groups is trivial. For when n is sufficiently large. So I mean when n is big enough. Okay, so to prove this, we are going to reduce it. It suffices to maybe I write in red. It suffices to prove that mu T is mu mu is T sorry what yeah, T is mu acyclic. So by lemma 1, so by lemma 1 and by lemma 1, by lemma and the Neopotent theorem. So by Neopotent theorem is here, that we already know that mu detects the Neopotence. So here we are proving that Kn also detects Neopotence. So we already assume that the Hurwitz image in this Kn homology are trivial, and so by the Neopotent theorem to show that X is Neopotence, then it suffices to show that the image of X in mu is trivial, and by the lemma 1 to show that X is Neopotence, it suffices to show that the T is E acyclic, and therefore it suffices to show that T is mu acyclic. Okay. And how to show this? We can use the Landweber theorem to construct some spectra called Pn. So
Oops, it seems that our speakers cut off. Yeah, maybe let's wait for a few minutes to see if you will be joining.
okay, now we can continue. Sorry about the interruption. Okay, now we are going to show that mu star T is trivial, and in order to prove this, we use the Landweber theorem to construct a spectrum called Pn, and the homotopy groups of Pn is G P is P and B1, B2, and this is B0, B1 until Bn minus 1. So I'm going to skip the details about, for example, how to construct Pn. That's going to be the tensor product with a bunch of something called Mk, which is the cofiber of Tk. I think you have seen that in Zhipeng's talk, I believe. So you can construct such Pn, and P0 is going to be the BP spectrum, the Brown-Peterson spectrum, and we know that the Mu localized at P is split as a lot of expansions of BP, and so to show that K is Mu acyclic, it suffices to prove that the BP, the P0 T is trivial. I mean, they're saying that T, we only have to show that T is P0 acyclic, or it's Brown-Peterson acyclic. Okay, so but now we can use the help of this Pn. Remember that P infinity is, so here I haven't defined P infinity yet, but P infinity is basically the limit of Pn, and it's actually equivalent to the Eilenberg-MacLane spectrum of Fp. And we already know that P infinity T is trivial. We already know this because remember that our assumption is that the Hurwitz image in Kn homology are trivial, and it includes the K infinity. So this is also the same as K infinity, right? The K infinity, the Morava K theory when n is infinity, it's also the Eilenberg-MacLane spectrum. And okay, so we have this. So now since it's the limit, and we already know that infinity 1 is trivial, then it should be trivial. it should be trivial for certain n. So there exists n such that Pn star T is trivial. So our goal, in the end, our goal is to show that this is trivial. The P naught star T is trivial. So that's our goal. Now we have Pn. So a natural thing to consider about is proof by induction, right? Decreasingly, we use this to prove that Pn minus 1 is trivial, Pn minus 2 is trivial, etc. One by one until the P naught star T is trivial. And that's our strategy in this proof. So we by proof by induction, decreasingly, And how? We are going to use a cofiber sequence, which is which is a map connecting between PM and PM plus 1. And remember that, so we are going to use the induction. So we assume that PM plus 1 star T is trivial. So we start from this assumption. Assume that. Then our goal is to show that this is also trivial. And since this one is, since we already assume that this is trivial, then if you tensor this cofiber sequence with T, then you know that PM tensor with T is isomorphic to PM tensor with T with VM inverted, because the last one is trivial. If you tensor with T with the last one is trivial. Therefore, by the long exact sequence, we know that the middle one should be after tensor with T. The middle one should be an isomorphism. So it means that the VM multiplication is invertible here, and therefore it's isomorphic. Since it's invertible, these two are the same. And then here is the magic. We know that PM is a module. PM is a module over MU, actually MUP. Then here we are going to consider this one instead. This is a module over MUP with VM inverted. So, I mean, since this PM star T is isomorphic to PM star T with VM inverted, so you can consider this one PM VM inverted and then star T. So by using this trick, then we can consider the MU VM inverse, since this spectra is a module over that. So we will prove an even stronger statement that T is MU P VM inverse cyclic. Sorry, MU VM inverse star T is trivial. Okay, so this one is stronger because PM VM inverse is a module over that, and now we know that this one has formal group, with height less or equal to n, m everywhere. And maybe you are still not that familiar with the the Johnson-Wilson spectra yet, but the fact that it has a formal group less than m everywhere, then this one can be deduced by this one. It suffices to show that T is EM acyclic. We know that E kind of is the universal deformation. So by some property, you can show that it suffices to show this one instead. So this one is stronger than that one. And okay, so what's next? The next one is interesting, that we are going to show. So remember that this will be used in the induction. So it suffices to show this for all m. Right? We will have to show this for all m. And now we are going to do induction the other way, increasingly. So we are going to show that E1 star T, E0 star T, E1 star T, they are all trivial one by one. And if we already know this, then we can use this statement to prove this induction decreasingly. But for this one, we're going to prove that increasingly, and to prove them increasingly, that reduces to the fact that Kn star or Km star T is acyclic. And that's exactly the assumption. Some people may be confused here because I skipped a lot of result. There's a result in you can see that from Lurie's earlier notes. I think that's the lecture notes on lecture notes 23 on the chromatic course, and that you can, to analyze all the EN thing, you can one by one, you can use the Km. Km is kind of like a slice of that, and you can use Km to do the induction. So that's the Kn En stuff, and this is our assumption in the very beginning, that the Hurwitz image of X in the Kn homology are all trivial. Now we use this. Now everything is reduced. Reduced to this, and so we are done. Okay, so I still have. Okay, great. I still have 15 minutes. Now we have shown that the Km homology detects the Neopotence, which is great. And what's even greater is that Km satisfies the Kunis theorem. I think there are very few ring spectrums that satisfy the Kunis theorem. I think only the Km spectra and the Eilenberg-McLean spectra of our field satisfy that because they are fields, and they are the very rare ones. Okay, and so here the exterior product can look like interior because of the Kunis theorem. We know that the Km homology of the tensor, of the smash product is the tensor product of Km star X tensor with itself over Km star. And and that's because this is a field, and you see that this is just like multiplication in this tensor algebra, and so therefore therefore x is x to n is trivial if and only if x itself is trivial. So you have a kind of a more a stronger result, which is the proposition that this is an if and only if, that the power of x in the homotopy group is trivial for n large, if and only if the image vanishes, the image of x, I mean not x to n, is x, vanishes for all m, and this is the if and only if. Okay, so that's kind of very good criteria. And now here's a remark from Rui's note that we can drop the requirement that x is p-local if we impose the same condition at all Morava K-theories for all primes. So we have a kind of a global or integral statement that the Morava K-theory for all primes together, they detect neopotence in the homotopy groups of any spectra. We do not require x to be p-local; it can be any spectra. But we need to combine all the Morava theory together, including all the primes. Okay, so that this is also useful. So now we have proved our claim that if E is a field, then E has the structure of a Kn module for some n. So this is kind of like a classification for all the fields that all fields are Kn module for some n. Okay, so that's the all we talk about Neopotent theorem. And next, I'm going to apply this to the proof of the thick subcategory theorem. So recall that. So I copied this from my yesterday's talk. Recall that T is a full subcategory if T satisfies three conditions. First, it contains the zero spectra. Next, is closed under the formation of fibers and cofibers. And lastly, it should also be closed in taking the retract. So if something belongs to T, then the retract of it, any retract of it should also also belonging to T. And here is a proposition that if T is a thick subcategory of p-local spectra, and Y is any other element in the finite p-local spectra, then so is the tensor product. So if only one of them is in T, then X tensor Y should be in T. Remember that yesterday I talked about the Balmer spectrum. This must remind you about like the ideal in commutative algebra, because if one of them is in ideal, then the any product, if the other element is in a ring, then the product is in ideal. So that's why the thick subcategory, they kind of like a ring, like an ideal. And you can talk about the Balmer, you can define the Balmer spectrum. And here is the thick subcategory theorem that you can classify all the thick subcategory of finite p-local spectra, that it must be one of them, one of the finite the collection of finite spectra for all for type n of type n of type m, where n should be greater than or equal to n. Okay. So I'm going to show you the proof. So the thick subcategory is equivalent to this form, that to show that the theorem, it suffices to show this. So if X is of type n, and it is NT, then you only have to show if Y is any spectrum of type greater than or equal to N, then Y should be also NT. So you can see that these two are exactly equivalent. Could you please elaborate why? Sorry, I think I'm going to answer the question later. Okay, so these two are equivalent. So we assume that T already contains something of type N, and Y is of type greater than N. Then we are going to show that Y must be in T. So here we are going to need something called the Spanier-Whitehead duo. I think in the summer school we haven't talked about this. Maybe some of you may not know. So basically, remember that in linear algebra you have like if you have a ground field K, you may have maps like this, and you also have like a V to V tensor V star tensor V into V. So you can use this map, and then you have So I'm saying that in linear algebra you can kind of pick a basis, and you can construct these two maps, and these two maps I think the second one is very natural. You can pick these two maps, so it satisfies the property that I think, yeah, it has the property that these two composites are identity, and the Spanier-Whitehead is trying to it's an abstract version of this. You can define something that looks like the dual of a kind of vector of some vector space, but here is spectra. Here is the spectra that you can still define certain dual of spectra, and it looks exactly like this diagram. And this is the requirement for the Spanier-Whitehead. That the dx is the dual, and dx behaves like the V star here. You should have a map from the sphere. So the sphere is like the field in the category, and the ground field. You should have a map from sphere into X tensor dx, and you also have another map from dx tensor X into the sphere. Okay, so that's what the Spanier-Whitehead dual is. It requires these two data and these two statement that they should be the composites should be identity. Okay, and if you consider the map E, then you induce an injection. So the injection is exactly, it looks like this, but it's not in spectra, it's in the Km homology. And because Km homology satisfy the Kunis theorem, then you can show that this is an injection. So this is an injection. And so what are we going to do with this? Since it's an injection in Km homology, then we can consider a fiber. We are going to call it F. So F is the fiber of E. And why is it useful? Because this map is trivial. We have a map from F to the sphere. In Km homology is trivial for m greater than n, because here we assume that X is of type n. So here, this is trivial for n greater than n. And we consider the composite. So here f is the same. F here is still the same, but we composite f with the map to the spaniel whitehead of y. And then we consider the G star. It is trivial for both m greater than n and also for m smaller than n. And that's because y has type greater than n. Therefore, we know that the Km homology for small m is also trivial. And so what are we trying to do here? We are constructing a map. We are constructing a map from f to y. We are considering a map from f to y tensor dy, which is trivial. It's not homotopic because it's not homotopic in EM homology. So this is trivial in KM homology for all m. And remember that we just proved the Neopotent Theorem, that the Km for all m, they detect the Neopotence. So there exists a power of this map, So this is G tensor K. We need to pick a K big enough so that G to K is trivial. So this is now homotopic. And we compose that with the multiplication y tensor dy, then we get so the y tensor with the spanning whitehead itself is kind of a ring spectrum. So you can multiply with itself. So in the end, you are going to get y tensor dy, because this thing can multiply with itself. So you can get this map. Okay, so this map is actually you can unravel it. It corresponds to this composition. It's f tensor f to k tensor with smashed with y, and you can keep composing f, and in the end you get y. So these two data are the same because let me write down f tensor k and you tensor with y, and then you can consider f tensor k minus 1 tensor f tensor y, and then here you replace this with f with y tensor dy tensor y, because of this, f can be mapped to y tensor dy, and then you map y tensor dy to the sphere, and therefore the whole thing maps to y. So now you have one less f here. So that's why it's k here, but it's k minus 1 here. So you can use that to get the whole composite. Okay, so and remember that this is not homotopic. This is not homotopic. The whole thing is also not homotopic. And so what's the deal about this? That you can see, since this is not homotopic, then y is a retract of the cofiber. So you consider the cofiber of this map. That's y over f to k tensor y. Then remember that the thick subcategory is closed under taking the retract. Therefore, it suffices to show that this cofiber is in the thick subcategory, and since it's closed under the formation of cofiber in fiber, you only have to consider the subsequent quotient here. Each time you have f to a tensor with y over f to a plus 1 tensor with Y. And these all are in the sixth subcategory T because we remember that the Y is defined by, because the F is defined by the cofiber by SP over F, and therefore this quotient is the same as the following, and it is a tensor. You can decompose it. It's the tensor with X. And remember that the sixth subcategory is like an ideal. We already know X is in a sixth subcategory. Therefore, this piece is also in the sixth subcategory. So I think maybe some people is already confused by the proof. But let me give you a not analog, maybe not a very close analog here. That remember that in the for example, in the polynomial algebra, G adjoint with X, we know that 1 over X is not invertible. But we know that if someone told you that X is Neopotent, for example, if X n plus 1 is trivial, is Neopotent, then you'll be able to do this construction of the inverse of 1 minus X, because X is Neopotent. I mean, this is like actually 1 minus X n plus 1 over 1 minus X. And you know that this is trivial, then that's the numerator is the same with 1. So that's a little bit analogous to the construction here. So you have Y, so you can compare Y to 1 here. Now you know that something is Neopotent. The map from this into Y is Neopotent. So you can replace Y with this. I mean, actually not. Yeah, you can replace that with this because Y is a retract of this. So you can replace this. So we are kind of playing we are able to play this trick just because of the Neopotence theorem. We know that something is Neopotent. So you can, and after you replace that with this, and then you consider the sequence of the quotients here. Each one of them belongs to T because of the X here by our definition of F. So this looks like a magic, but we are able to do this magic just because of the help of the Neopotence theorem. So that's everything about today's talk. We have proved the sixth subcategory theorem. If you are interested in more detail of the proofs of some details I skipped, you can read the lecture notes. And actually, I also use something from previous notes for including the lectures 23, I think. So yeah, it's great notes. And so if you are confused at some point, you might ask the question now, or you can read the notes. Okay, so that's the end. Thank you all for listening to this talk. Sorry, I'm a bit over time.